Favonia about yet another library about homotopy type theory, but this time in Agda.
All right, so I think I only have 15 minutes, so let's be fast. Oh, what? Oh, also I'm hungry. Okay, so anyway, so you won't be too long if you're hungry, so I'm with you. So let's introduce this. Like years ago, I was at IS and I also at CMU like learning the hard stuff. And at that point of time, only the Carnegie and Agda only the Carnegie and Agda are the proofs are ready to use immediately, and I want to do experiments. So for some randomized process, I pick Agda. So our goal is my goal is to experiment some of the things I learned in Parlang and put them into code and in Agda to type check, try to type check it at least. And then, of course, like for example, when you're trying to do that, then you also have to prove lots of other theories. Like at one point, I want to do a little bit of cohomology theory, and I need to do a little bit group theory in order to finish that. So this is the goal, but in the middle process, we also prove lots of other things. So that's basically how the library is structured. Next page. So the one thing I want to emphasize is that it's really decentralized. So yes, there's a big one there that is under the hard group that are half refractory, but there are also all sorts of forks or like older versions of experiments. For example, the experiment I did was actually under my account, then I abandoned that and I joined Kian to do another thing. We copy each other's code very frequently, and we also and it's not even forming a DAG. Like there's a lot of circle. I copy yours and you copy mine, and we're all cool with that. So anyway, the porting theorems and forking are very common. And we're also trying to, for example, I think, it's not this yet. I think there's one Agda deployment I really want to merge into the first one. The first one is the main one, so if you want to have some thing for reference, I think you can consult the first one, but there are also all sorts of other things that I don't even know of. All right, so this is, I think, the one core part of the Agda that you can really just create your own part. But since I'm not the authors of all this, so I will have to just focus on one particular one. And even with that particular one, I'm only contributing to a portion of it. So I'm not going to really introduce to you the entire picture, like what exactly has been done there. But I can list lots of them. So we have recommencing. I'm now working on a generalized version where the truncation is replaced by some locality condition. Of course, I don't have time to. Oh, it's only 5 minutes. Okay, so we have the total space of the half vibration, and also the 3x3 lemma, which is basically a coherent condition about a push out that can be used to prove the total space of a half vibration. That's why I listed in the central. And there's also a Van Kempen theorem. There's also something in the cohomology theory about the Mayer-Victoria sequence, basically from the axioms you can prove that there's a sequence. There's also a cubical reasoning that so you have identity type, but often when you are trying to code it out, you realize you actually want a square. You want to talk about square directly. Even though you don't have even though you are not using cubical type theory. Now, for a long time ago, we know that the cubical structures are so wonderful. So I think this is mainly done by Licata and Gian, Dan and Gian there. And also have fundamental. It could be this is actually a correlation of the specialized version of recurrency, but we also have the different code for that. And we have element plane spaces and so on and so on. So there are just so many things. So these are the authors that people have contributed to the Agda heart. I want to point out that I think Mike Shulman is the only person who contributed to all, except including Unimas maybe? I don't know.
Including Unimas, yeah. I don't know about Unimas, no? I mean, I don't know if any traces of it. Maybe there was something back.
Oh yeah, I still have to write some code to achieve this.
Completion. Wasn't he in the rest completion thing? Rest completion.
He didn't write any code, but he contributed proof.
Okay, so this is just fun stuff. Okay. So there are lots of things that going on here, and also prove, as I said, all the other things are needed in order to show these results. But I won't have time to go into any detail of this, so I'll just talk about like what kind of features we are using. So Agda, roughly speaking, is a multi-level type theory style logic or programming language, depending on how you view it. And it also has lots of crazy things, like inductive, recursive types, or very complicated mutual definition. They are all fine, right, as long as you can convince Agda. And it has syntactically, so this is not directly about the proof strength of the type theory, but it also makes differences for Agda from other proof systems, which is a powerful mixed parser. I can probably show you part of it in the end if I have time. And there's a pattern matching, and there's a very powerful dependent matching. I've seen so many camps that they have implemented Agda style dependent pattern matching. But when I look at it, none of them so far, I think, are as powerful as the one in Agda right now. Agda has so many weird stuff that, I don't really have time to go into. And we also have the universe polymorphism. And this version, the one in Agda is actually the second order polymorphism. Now, not only that you can have a quantifier talking about the order universe, but you can also pass around something that is universe polymorphic. So this is, I don't think this is really well understood, but they put it in anyway. So this is the spirit that, I'll have a slide for this. So for automation that people might care about, we only have unification. I think in some regard you can regard it as some kind of automation. And we have a little bit of literal overloading, like the 1 can be treated as an integer and a natural number, and also the homotopy level or truncation level. And we have very few tactics. It really depends on your definition. According to some definition, this is actually none. But I don't want to really go to a detail. Basically, you can pretend that there's no techniques. All right. So the high inductive type that has been a heated topic. So we were using dense shake that the boss has talked about in similar to Carnegie, like you have a private data type. But then in Agda, probably has too many features and the pattern matching is too powerful. It's really difficult to prevent other people from proving false, or true equal to false, 0 equal to 1. There's a very lengthy document written by Guillaume saying that you have to apply this trick. You have to kind of define it in a private way, and then have another data type which take an element as a construction, and then have another one which construction just take a function from unit to unit. And all of this to prevent also weird usage of the pattern matching. I think in the end you need to apply 3 very messy hacks to prevent all known attacks, and we're still not able to prove it's correct. So I think this is the most civilized version. Let me just show you. So this will be the only part, Agda code that you will show in my talk. I hope we can kind of go through it. So then right now, the definition. Well, let me do a disclaimer. This is a real Agda code that will just run. But we are not using it right now because right now the circle is defined as a suspension of bool, if you know what it is. But I think this is still a very good example that I want to go through. You can define circle this way, just that we are not doing that right now. So circle is all postulated. I postulated that there's something called circle, and I postulated that the base is inside that, and there's a path between them. So from the base to base, and then I want to define the animation rule. Basically, that given these inputs, now if you know how to do with the base and you know how to do with the loop, and you say that you postulate that there's an elimination function. This is the eliminator from the circle to the theorem you're trying to prove. And then, but we want to also compute points. So this is the thing I'm talking about, the new feature we are relying on. You can postulate that, okay, there's a reduction rule for base. And so this line is really to hook this reduction rule into the Agda. Saying now whenever you see this, F applied to base, you should reduce it to base, right? The proof element. And also still have to postulate that this proof is that. Right now, the current Agda kernel, you can also phrase it as a reduction rule and hook the rule into an Agda so that it will compute base and proof. But we are not doing that because I don't think it's really well understood yet. And also the hardbook version only has the definitional behavior on the base, but being only homotopy on the loop. So we are using this version. So we are kind of, in some sense, very conservative, but in some sense also very exploratory, trying different things. So idea basically is to use this new feature to achieve the same effect of the dense streak without those hacks. Those hacks are really appalling in my opinion. All right, so this is how we do the Untitled test right now. Okay, so this is really the point I want to bring up because I think this might determine whether you want to use Agda or not. It's not well understood that how the entire language is working. We don't really have any sort of good consistent guarantee that, because a good consistent guarantee will be maybe there's a core language and you can prove that as long as you believe some very large ordinal number and ordinal, then you can prove that it's consistent or something like that. But in Agda, it's not even clear what kind of core language is, and not to mention the theorem. But anyway, it's not well understood. Many individual features have been proved. For example, that we have a without K, and you can isolate a part of the Agda, and then you can prove that the unification algorithm is fine. But then it's then coded in Haskell, and no one has really didn't go through very rigorous auditing process or something like Tom did that using an unproof system to prove the correct unproof system and then make the data. So none of them has been done. So personally, I don't really trust the kernel. I trust Agda proofs, but not the kernel. I trust that if you're using it in good faith, then the proof should survive. For example, actually I have this example. So there's a naive set theory. So we can prove something in terms of a naive set theory. And then people then realize that there's a paradox. But nonetheless, I think most proofs in the naive set theory is still fine. So that's basically my model usage in terms of Agda. I don't really trust the kernel, but I believe the proofs. So the model usage here is really highly dependent, and we really like to explore things. And you can see that every month there are some new features or trying to get more computational behavior and so on into Agda. All right. So let me show you some statistics. So right now the structure is that we define the Agda hot library into two parts. So one is the core part and one is the interesting part. But the definition is arbitrary, but we try to make it reasonable. So for example, the definition of a circle will be in the core, but the brackets messy will be in the I don't think it belongs to a code. Anyway, okay, so we also have the same mechanism as a cloud that we're using Travis to continuous integration. What it means is that whenever you push something on GitHub, then there's an independent server running the Agda and checking everything. So we want to make sure that no one is destroying the correctness of proof. And the thing is that it can be checked at least on this server 20 to 30 minutes. There's a wide range. Don't ask me why, because I just look at the time, the number of minutes that it needs on traffic is not a constant. So that's the best I can do. So yeah, there are some statistics about the lines of code. Actually, the tool I use doesn't recognize Agda. I have to say that pretend Agda is Haskell or something like that. So the numbers are done by pretending Agda is Haskell. Yes, I think this is the last page. Yes. Oh, okay. So any question?
Thank you. Everyone's hungry.
So why do you have this decentralized model?
I think that people just want their own repository for many reasons. Some reason I heard of is that they want to do something and they really want to change the code library, but they also don't want to pollute the main one, the Agda, while they are doing something else. And then so there's a fork.
So how many time do you spend on porting from one library to the other?
I actually didn't do much porting from other libraries. I did a little bit, but not much. Sometimes I did post something from Bing, but that's more like understanding it and recording again. I did indeed some porting from the older version of library to the newer version of library. For example, actually I proved bracket message twice, config space twice, or maybe 3 times maybe. So the rewriting is interesting. We rewrote the entire library to use cubical reasoning. So you have a path over time and so on. Does that answer your question?
Yes.
One question. What in this library couldn't be done, for instance, in lean topics?
I think it can also be done. That's why we are copying each other code all the time. Shows that in principle, yes.
But maybe something you would say it's more elegantly done in Agda or in lean, or I don't know. Would you be able to
Because I can
compare
use
the
all
ergonomy
these.
of two systems?
Amazing. So first of all, I can use all of these systems. So if you want me to code that, I can also do that.
And that's why I ask you: is there any feature of Agda or of lean that you lack?
Which one gives more readable proofs
Yeah, for instance.
mathematicians?
Or for mathematician,
Yeah.
I'm not able really to say I'm a computer science and any code is fine. And the syntactical whatever, like, as long as you can write down as a string, I can pass it.
So for instance, both lean and the hot library use some sophisticated type inference, for instance with type classes like mechanism, and as far as I understand, you don't have this in Agda.
You could have that, you're not using it.
Okay.
So Agda is supposed to limit form of the type classes.
But do you think it's a good thing not to have them, or it's useful and you like them?
Having them, so mechanization, in my opinion, is a balance of like three factors. There is machine time, the type checking time, user time, that how much code I have to writing, and the strength of the mathematical theorem. So I don't think there's a perfect solution. I think you have to sacrifice the other to achieve that. You have to, for example, the type classes, if you're abusing it, if you put a type class everywhere, I think one version of the R library is trying to use the type classes or what is called instant argument in Agda to find the natural homotopy level, natural truncation level. For example, when I say circle, I should already know that is the level 1 or something. So you can use that, but if you use it too much, then Agda will be slower, because whenever you see that, oh, how should I find the proof of this truncation level, you have to go through all the possible proofs that are available and that in that context, and to try to figure out whether there's a way to make a proof. And that could make a type checking slower. Does that answer your question?
I think the best predictor of what proof assistant was used for something is just who wrote it.
Oh, I'm not using about the best proof assistant.
No, the best predictor of like for Agda versus
for this spectral application.
Yeah.
Is there some identified feature of one or the other proof assistant?
Well, I think
Well,
if
actually,
something was,
maybe I can ask a particular thing which can also somewhat close to your question. How about the Serre spectral sequence? Because I find this kind of very surprising, and
well, give me enough time and money for survival. I can probably pull the
money to
entire
do what?
survival.
Survival.
I think I can put whatever they did into Agda. I need time. I also need more time to optimize the proof so that Agda won't spend like 1 hour on some proof. That's more engineering has to be done in order to make a practical Agda proof.
I think it looks like a great